can we look at that and see that, yep, that contains our uniform circular motion solution? What would that look like? What would the uniform circular motion solution look like? Then this would be 0. The radial distance isn't changing, and we just balance those two things. And I hope that's what we did up there. So that's where we started with our uniform circular motion. Now we have to admit the possibility that the radial distance is changing. Okay, now I promised that we would try to make some mileage out of the fact that the angular momentum is a constant. So the angular momentum, mr squared theta dot, is a constant. And I can use that to get rid of this term, or the theta dot dependence, right? I could solve the angular momentum for theta dot. And I can substitute that into the equation of motion and get rid of theta entirely, right? So then I would have r double dot minus L squared over m squared r cubed is equal to minus gm over r squared. I have one r, and then I have r to the fourth in the bottom. So r divided by r to the fourth is r cubed, right? Is that right? Shout. Where? So this term, theta dot squared, I need L squared, m squared, and r to the fourth in the bottom, but r on the top. So r divided by r to the fourth is r cubed. So now it's only a function of r and time, except that I'm trying to test the hypothesis that an ellipse solves. So I know something about the shape of the orbit. I know that r, this is what I'm trying to test, that r is equal to a 1 minus epsilon squared over 1 plus epsilon cosine theta. So if I could just evaluate the second time derivative of that, I could test to see if it works in this equation. Are you beginning to get a sense why Newton invented calculus? It was handy for this sort of stuff. Okay. Well, the only way I'm going to get to the second derivative is by trying the first derivative first. So I need my friend the chain rule again. And this is a derivative that we all should be able to compute, because it's, let's see, it's a constant on top. Help me out. Now what? I'll give you a minute. Work it out. It's useful practice. We need to take the derivative of that expression with respect to theta. So do you agree with that? So I have to use the power law. I had the denominator, so this is this quantity to the negative first power, so I'm going to get the negative second power. But then I have to differentiate the denominator with respect to theta, and that gives me a minus epsilon sine theta. And the last term is a theta dot, which, if I were clever, I might want to use this relationship on, because it's going to simplify things a lot. So let's try that. dr dt is equal to, okay, the two minus signs are out. So I have a 1 minus epsilon squared. I have 1 plus epsilon cosine theta in the denominator squared from before. I have epsilon sine theta. And now theta dot was L over m. And now I get to write r squared in the bottom. Do you see what we're doing here? Theta dot is going to get replaced by L over m r squared. But I don't want to write r. I want to use what I know about r, because it's going to kill a lot of stuff. So I want to put r squared down here. That means a squared, 1 minus epsilon squared squared in the bottom. And on the top, 1 plus epsilon cosine theta squared. Now you're supposed to lo and behold. Are you lowing, Carly? Yeah, she's lowing. What happens to all the angular dependence almost? It goes bye-bye. So this term here wipes out that term there. dr dt, I just have to collect some constants, I think. Oh, I'm going to have a sine, right? I'm going to have a sine of theta. So epsilon sine of theta. I'm going to have an L on top. And what do I have on the bottom? M, A, and 1 minus epsilon squared. Why is that so dang nice? Because I have to take another derivative, and this is way easier than the one that I already did. So it means that I might actually be able to finish. So now when I take d2r dt squared, that's d by d theta of dr dt, then times d theta dt. But d by d theta is easy of this expression. That's just L epsilon cosine theta over ma 1 minus epsilon squared. And now I have to multiply that by theta dot, which is L over mr squared. Okay, we're almost there. I can almost taste it. So all we have to do is stuff that in here and see if it works. So we have L squared epsilon cosine theta over m squared a 1 minus epsilon squared r squared minus L squared over m squared r cubed equals, question mark, minus g m over r squared. Is that looking promising? Let's see. Seemed like I want to wipe out like 2 of the r squared. You know, like the r squared would be a good idea. So So let me pull out, in fact, let me multiply the whole thing through by m squared r squared. So that leaves me with L squared epsilon cosine theta over A1 minus epsilon squared minus L squared over R is equal to minus G m squared. So one last substitution, I now substitute in what I had for R, and I get L squared epsilon cosine theta over A1 minus epsilon squared minus L squared over A 1 minus epsilon squared times 1 plus epsilon cosine theta is equal to question mark minus G m squared. So what do you think? Does the left side have any angle dependence?
No.
The cosine terms wipe each other out, and so we're left, oh my God, we're left with L squared over A1 minus epsilon squared is equal to G m squared. Or, put another way, L squared is equal to G m squared A 1 minus epsilon squared. That is, as long as we pick the right value for angular momentum L, we will have solved. This works. The left-hand side is equal to the right-hand side, and so an elliptical orbit is consistent with Newton's laws. So that's Kepler 1. What a lot of work for Kepler 1. Kepler 2 and 3 are a lot easier. Yeah?
What exactly do you have to choose to make that?
Well, this is just saying for the elliptical orbit that's described by the semi-major axis A, and the eccentricity epsilon, this would be the value of angular momentum squared. And that will go around that ellipse. Okay? Okay? Do you agree all the stuff on the right-hand side is just constants? So this is consistent with angular momentum being a constant. Yeah, Ian? So it has an equal question mark. This has no theta dependence. So if I was left with any angle dependence on the left-hand side, I'd be hosed. I would have demonstrated that doesn't work. But the cosine terms exactly wipe each other out, and I'm left on the left-hand side with just some crummy constant is equal to a constant on the right-hand side. So that allows me to say, the left crummy constant, L squared, has to be that. So in terms of the shape of the ellipse, which is defined by A and epsilon, this must be the angular momentum squared for an orbit. So it worked. So the question mark now goes away. It worked.